It's time for our third autonomous navigation video. Today we're going to talk very briefly about the correction part of state estimation. Remember what we're doing. We're trying to allow our robot to autonomously navigate in the world to track some desired state, maybe x, y, theta. We've been talking a bit about the estimator and the sensors that feed into the estimator. And today we're going to talk about state estimation with correction. Remember, with our two key steps, we have prediction that predicts where a robot might go, but then we'll probably have some form of correction, and the state estimator must fuse the predicted measurements with the corrected measurements. And as noted in the last video, typically errors associated with prediction will grow unbounded, and errors associated with correction will not. Well, that means that our correction sensors must be absolute. They must be with respect to some global coordinate frame, and that's typically what we do. Now, most of you are probably familiar with GPS, and we're not going to talk too much about GPS. So GPS, which stands for Global Positioning System, is something that most people are pretty familiar with. You've got them in your phones and now watches. They were originally developed for the US military, but now they're being used by all of us all over the place. And you can actually buy and sell them for much, much less expensive than they used to be. And they bank on the fact that we have 24, or now more than 24, satellites out in orbit sending us signals to our receivers in our handheld watches, devices, whatever they may be. This is the basic setup that was set up quite a while ago. We've got these satellites, right? And they're transmitting signals so that if I'm driving my old school car here and I've got a GPS receiver, I can receive signals from many, many satellites. Now, what you might not realize is that there are these monitoring stations and master stations around. And these monitoring stations and master stations are used to figure out what these GPS satellites are up to and actually communicate with these GPS satellites so that the measurements or signals being sent down to a user, someone with a GPS receiver, will have the best data it can. So what's going on here is that the receiver in your car and in your hand or in your phone, whatever it may be, is used to measure the time of flight from all those satellites. Now this requires time synchronization between the satellites and the receiver. It also means that we need to know the position of the satellites, and we need to know a precise measurement of that time of flight. All right? And there's a whole bunch of interference with other signals that we have to deal with and must overcome. Now, the time synchronization is done with atomic clocks on each satellite. And those ground stations I mentioned a couple slides ago, those ground stations are actually used to monitor and help synchronize all these clocks. Now, we need to know the locations of the satellites as well. Now, the ground stations are also used to help monitor the positions. The master station will analyze all these measurements and transmit the positions to each satellite. So now, each satellite should have pretty well time synchronized clock and know its position. And it can actually send this data and transmit it to our handheld receivers. So how does all this work from the receiver point of view? Here's a submarine, maybe it's surfaced out in the ocean, and it has a GPS receiver. And from each of these 4 satellites, it gets information about the satellite's position, what time that satellite transmitted a signal that was received here, and it gets that from all of these satellites. This is very important. It needs a number of satellites, and from each one of them, it gets a position or origin of when the signal was sent, the time it was sent, and because it's got its own clock, it can figure out the time it was received. Now, knowing the time a signal was sent and received, and if it knows a velocity, it can then back out the distance between the satellite and the submarine. Now, this yellow circle indicates a circle of equidistance from the satellite. Now, if all satellites transmit such signals, and we know the distance then from all these satellites, the position of the submarine must be at the intersection point of all the circles. So now we have a method called trilateration that will give you a measurement of your GPS receiver's position based on the distances and locations of all the satellites. Of course, there's going to be errors associated with each one of these positions of satellites and distances to satellites. So these wonderful circles that were all intersecting in the last slide actually have errors associated with them. And the overlap will produce one large error. How bad can these errors be? Here's an example of some of my research. One of my students was driving down the road. Now, this day looks pretty good, looks pretty well mapped up with the road. These are his GPS measurements. Let's look at this particular image though. It looks like he was driving on the wrong side of the highway, flipped over to the right side of the highway. In actual fact, he was not doing that. This was one of the common GPS errors. Now, many people guess maybe it was under the bridge, maybe not. What actually happened was only 3 satellites, and then at some point, the GPS receiver in the car was able to detect and get measurements from a 4th satellite. And with this additional satellite, it got much better accuracy of the vehicle's position. There's a whole bunch of errors associated with GPS, atmospheric effects, things like this, that you can actually go and study and learn about. Point is, at this point, you better know that GPS does not produce millimeter level accuracy without a whole bunch of conditioning, much of which you will not have in your hands for this particular class. Here's a general list of these errors. You'll notice that when you're driving around the city, your errors jump. That's because you have multipath. All those signals being transmitted to the satellites start bouncing off buildings. Key takeaway is that we've got meters of error with our GPS positioning. Now, something else to note is while GPS is ubiquitous and everywhere in our daily lives, it's not for the underwater world. In fact, those GPS signals being transmitted by satellites do not really penetrate into the ocean or into lakes or even into swimming pools. Hence, we've built acoustic positioning systems. Typically, instead of satellites, we put beacons that transmit sound waves because the sound transmits much better through the water. And we will have receivers on our robots. And we use all the same principles of GPS, only with underwater acoustic waves. It's not nearly as high bandwidth, and it's not nearly as accurate as our really accurate GPS measurements. But regardless, these work pretty well and have been used all over the place. You can argue what's more difficult, setting up satellites in space or anchoring transponders to the bottom. Both have their issues. In this class, you might attempt to actually build such a positioning system, but be warned, this is quite a task. Just to get the acoustic signal conditioning done and working well will be a major effort. Now, to recap, we talked a lot about prediction measurements and even just went through a couple correction type measurements like GPS measurements. But don't forget, at some point you need to fuse them. Now, you could average them. You could guess at which one was better and give more weight to one, but I'll remind you what I said a couple videos ago. There's actually quite a bit of effort into making these state estimation algorithms. There are things like Kalman filters, particle filters. If you look around, you might find some of these in some of our technical elective engineering courses. But these can get pretty sophisticated pretty quick, especially if you're estimating high dimensional spaces. If you want, you should probably find someone like Prof. Clark, maybe Prof. Spencer to give you guidance on these things, maybe even Prof. Spute. There are a bunch of professors who know about these filtering techniques. Just ask around, or you can learn about them in your tech elective courses. To summarize, what's great about some of these correction sensors is they provide absolute position measurements, ones that won't just accumulate error over time. However, they come at the cost. You're going to have to set up some infrastructure in your environment to use them. And don't forget, there are many state estimation algorithms out there, even though we're not covering them in E80. And these algorithms are used to optimally fuse the prediction and correction sensor measurements.